All right, antiderivatives. So when you think antiderivative, pretty much this is really just another way to say integration. So maybe we could put AKA integration. Because really what we're doing when we do antiderivatives or integration is the question that we're asking ourselves is what function would I have to take the derivative of in order to get f of x, or a sort of backwards integration. So question, what function would I take the derivative of to get f of x? So ultimately that's what we're doing when we integrate, is we're kind of taking the derivative, but we're just going backwards. So probably one of the more useful equations, and it kind of works as a good example, is let's say you want to integrate or take the antiderivative of x to the p dx. Now, we're saying in this case, think of it like this. This dx just means we're integrating x of p, or x to the power of p, with respect to x. So, and this kind of comes in handy where, like, if you have another, like maybe you have y xp or something like that. This is specifying that we're taking the integral with respect to x here. So, if we do that, then all that we have is you're going to take your x, you're going to take the exponent and add 1, and then you're going to divide it by this up here, this p plus 1. And then last but not least, anytime you integrate, you're always going to have to add this plus c. And now what this plus c does is this says, well, there's some constant here. Now the constant could be 0. But you have to remember that if you since we're doing integration, or since we're doing derivation backwards, the derivative of some constant just equals 0. So that wouldn't show up in this x to p, right? So because of that, we have to make sure to add, it's kind of like a nice way to jog your memory, that you could add some constant here, which wouldn't show up. So let's take a look at an example that will kind of maybe illustrate really what we're doing. Oops, I guess that's not an example, but this is the real example down here. So let's say you want to integrate 3x squared dx. Now, just like with derivatives, if you have a constant, you can move that constant out front. So you can actually rewrite this as 3 integral x squared dx. All right, now we just use our handy dandy formula right here. The 3 stays the same. So I've got x squared, so you add 1 to squared to get it cubed. Then whatever value you put up here, you just place it below in the denominator. And then don't forget to add your c. So now, looking at this, we say, okay, well, the 3's are cancel out, so I get x cubed plus c. Now, the nice thing about integration is you can always double check yourself, because if you take the derivative of this, it should get you back to that, right? So we've got dx of this, of whatever we had, so x cubed plus c. Well, the derivative of x cubed, that's just going to be x squared, 3, right? 3 comes out front. And then the derivative of c is 0. So voila, I checked myself, right? So 3x squared, 3x squared. So really that's all that we're doing. We're just going, you can go back and forth from derivatives and integration. Now, one thing to keep in mind too, this will be And so this example's to that one. So this is another example. Just keep in mind that a lot of times it can be really helpful to simplify, at least at this stage in the game. Now later we're going to learn some, I don't know, not really tricks, but I kind of call them tricks, that'll really help you out in terms of taking the integrals of stuff. But for now, just with the basic rules that we have, remember that oftentimes it can be helpful to simplify things. So for example, instead of this, right, we'll go ahead and use algebra and FOIL that out, right? So we're going to have t to the fourth there, and then we're going to have 2t squared, and then we're going to have 1 dt. See, now I can take this integral fairly easy, because it's going to be the integral of t to the fourth plus the integral, now this 2 comes out front, t squared plus the integral of 1, and then all of these are dt. All right, so keep that in mind. That's there. All right, so looking at this, we're going to have t to the fifth over 5 plus 2 times t to the third over 3 plus integral of 1. That just goes to t. And don't forget, make sure that you add this constant there. All right, and then maybe one last step, if you wanted to really simplify it, 1/5 t to the fifth, 2/3 t cubed plus t plus c. And there's a couple other rules that are in the chapter, but this hopefully will kind of give you the gist of what it is that we're doing. Because you have these with trig functions, with exponential functions, with logarithmic functions, all of that. And then the last thing that they go over, and this is kind of the connection, the physics connection, the relationship. Remember we talked a little bit when we do derivatives, right? If you have a position function and then you take the derivative of it, you'll get the velocity. And you take the derivative of that, then you get the acceleration, right? So it works backwards then with integration. So if you do integration, if you start with your acceleration, you take the integral of that, you'll get your velocity. You take the integral of that, and you get your position function. So like for example, again, well, this is just how you can move back and forth. Now you kind of have the complete picture. You can move from position to acceleration to velocity really easily, just using derivatives and integration. So for example, the acceleration due to gravity is what, 32 feet per second squared, right? So I've got 32 feet per second squared. Well, if I take the integral of 32, that's going to give me 32 times t plus some constant c. Now that constant, whoa, I'm running out of room here. Sorry. This is going to be kind of goofy for a second, but we'll save some paper instead of flipping the page. All right, so I've got 32 times c, so this is my velocity, right? This c right here, well, remember there's a constant, so I'm just going to go ahead and say, well, that's going to be my initial velocity, right? So then if I took the integral of this, then I'm going to get 32 times t squared over 2 plus v naught of t plus, don't forget that constant, right? Well, and then this gives me back to the position. Remember the position equation was 16t squared plus v naught of t plus s naught. So you can see there's a lot of applications here when it comes to physics. We're going to learn a lot more about this in the coming chapters. But this chapter is just kind of a way to start introducing how we can move back and forth between derivatives and integration and what exactly kind of the foundations of it are.